Okay, why don't we get started? I'm just going to make sure that you can hear me in the back. Yeah? All right, good. Okay, come on in, have a seat, let's get started. Okay, welcome everyone. This is ECE 408, CS 483, CSE 408. Hopefully you are enrolled in one of those three courses. It's actually the same course, cross-listed, so hopefully you're in the right place. There's a lot of you, and just a few of us, just one of me. If there's any issues with, what you can see on the board, on the screen, or you can hear me, just raise your hand, let me know, so that we don't, we aren't disrupted too long. Okay, so for many of you, this is or some of you, I don't know if many of you, but for some of you, this is your very first course here at the University of Illinois. So welcome to you. I feel special that I may be your first instructor here, so welcome. For many of you, you've been here as an undergraduate or as a graduate student, and I welcome you too. So I think this semester is going to be very special for you because this is a very special course. What I'm going to do today is kind of help set the stage for what this course is. And many of you are here because you've heard, well, it's a pretty straightforward, easy course. And it is. All right, there's nothing super challenging here, except that for many of you, it's going to be a shift in the way you think about things. And you'll struggle through that. Okay, you're not going to spend nights and nights on long homework assignments in this course. There's programming assignments, a lot of them. In fact, almost weekly, there's going to be something due. I like to think that this program is this course is conceptually challenging in the sense that everything you've done up until now, you've coded in a particular way, and now we're going to introduce you to something that's very different from the way you've done it in the past. For some of you, you're going to make that transition very easily. For the bulk of you, and this is from my experience teaching this course for many, many semesters, for some of you, it's going to be a challenge. And you're going to try 1 week and fail, and try another week and not fail so much, and try a third week and slowly start to get it. Okay, so I'm probably speaking to a majority of you at that point, right? You're just going to have to struggle. And you'll get there, trust me, because it's a very different way of thinking. So, with that in mind, let's kind of go through this and get you introduced to the course. Okay. Before we begin, I'd like to always open up with questions or comments. Not that I expect you to have any yet, but anything. All right, great. So, you look around, there's a lot of people here, probably around 200 students here, okay? And I was telling my wife this morning that, well, I've managed to not have COVID at all, ever, that I know of, but I expect to get it today. So, well, what can I do, right? I don't expect there will be 200 students in this course, in this lecture, like 3 weeks from now. And the primary reason is that this course, even though we do meet in person, everything is online. It's entirely digital, okay? And that's in part because we have a lot of students that are online students, that are not here on campus this semester. Some of them are in Chicago with the City Scholars Program. Some of them are in China at the ZJUI campus. So, I'll be here Tuesdays and Thursday mornings lecturing. The other course instructor teaches on Tuesday, Thursday afternoons, yeah, we're going to be here doing it live in person. But, you know, you don't have to come. All the lectures will be available. All the slides are there. All the material from previous semesters there. So some of you will find value in coming and talking to me while we lecture. Great, show up. But I don't expect this many students to be here. Nor should you feel bad about not coming. Okay, it's just life. So, I'll be here in person, but everything is available online. The lectures, recorded, posted, slides, posted. In fact, the slides, I have a habit of posting the slides probably like 15 minutes before we all meet here. Okay, but they're there, right? If you want to follow along while I'm going through them, they're there for you. Okay, and oftentimes what I'll do is I'll make notes as I go through this, right on my iPad. And if I have my act together, I'll post the annotated version as well for you. Okay. We have 7 labs, really 8 labs, and 1 project. Okay, and these are all coding. So there's, you should expect a code in this course. In fact, I'll say a little bit more about that shortly. And these are all due on a fairly regular basis. I will show you the schedule. And they're all online, right? You don't have to physically turn anything in. And then we also have 2 exams that are in October and in December. And those exams are also online. So no need to show up. Okay, so that's kind of the process here. All right, so I'm going to introduce myself and the other instructor in a moment, but in case you don't know me, Sanjay Patel is my name. The other course instructor is, I'm going to butcher his Ukrainian name, Volodymyr Kindratenkov, Vlad as we call him, Professor Kindratenkov. And I'll introduce him as well, but he and I have been teaching this course together for the last, 3 or 4 years. So we work really well as a team. He teaches the afternoon lecture. So if you choose, I don't like this guy in the morning, he's kind of boring. You can always go to Vlad's lecture in the afternoon if you like to be there in person. And there are many of you, as I pointed out before, and few of us. So we have a very strong set of teaching assistants that are helping us with the course. Okay, they're there as your primary resource for the programming assignments. I'm not going to help you debug your code. You can ask me and I'll try, and trust me, it'll be the worst experience of your life. Okay? Because I'm going to struggle through it just like you. I'm happy to do it, by the way. I learn a lot. I'm not saying that don't do it, but I'm saying that if you're pressed on time, probably the TAs are going to be a better of use to you than say I will. Okay. The TAs are there. In fact, you'll get to know them throughout the semester. So let me tell you a little bit about myself, because you're in my section and you should know me a little bit. I have been here on the faculty since 1999. I'm tempted to say that probably before some of you were born, but that just makes me feel pretty bad. But I've gone there already, so yeah, there we are. So I've been here since 1999 on the faculty, doing work in pretty much the topics we're going to discuss here. I do work in computing systems, architecture, and I've done that for quite a while, computer vision and ML, all kind of looking at that intersection. Some of you might know me from this textbook, if you're an undergraduate here, and you ended up taking ECE 110 or 120 or 220, you're familiar with that textbook. and hopefully thankful for it. But more recently and more kind of what I've been spending a lot of my time and energy on is building companies. And I just want to share something with you, not in any boastful kind of way, but I put this together kind of to make a point to you. Okay. Over the years, what I have done is helped create companies that in some way relate to this course. And that's really what I want to tell you about. Okay, in 2004, I was part of a team that created this company, Agea Technologies. We built a chip. It was the world's first 80-core chip. And I'm going to talk a lot about that in this course because we built it at a time before GPU computing became a thing. And we were really part of the formation of what is now CUDA. Okay, so part of Agea, I was the chief technology officer for Agea. We were making that chip. And if you care to know, the chip was actually, like we have graphics chips, GPUs, which hopefully you're familiar with. We were creating a physics processing engine to essentially simulate all the physics in virtual worlds, in 3D environments, in video games. Okay, we started that company in 2004, and in 2008, that company was acquired by NVIDIA. One of my students, he would have been in 408, but 408 wasn't a thing back at that point. GPU computing was not a thing. One of my students, Chris Lamb, master student, joined me at Agea. He was part of my team. We had built some of the compiler technology. He was part of the compiler team that we're using for that for the Agea chip. And after the NVIDIA acquisition, he stayed at NVIDIA, and now we're looking at about 15 years later. Chris is the vice president of CUDA at NVIDIA now. Okay, so he's a special guy, very special talent, but he got his start here at Illinois with me through Agea, and he's carried on. I'd like him to come and give us a guest lecture at the end of the semester, but he's a busy guy, so I'm not sure he will, but someone from his team most certainly will. Okay. After the Agea acquisition, I created a company here called Personify, which I'm sure no one has heard of it. But if you've ever used a Zoom conference and you've changed your background, well, that technology came out of Personify. We invented it. This was way, way, way before the COVID pandemic, way before anybody used Zoom. We created that company in 2011 with Quang Nguyen, Dennis Lin, Simon Van Steen. Again, students of mine. They were around before 408 was a course, but they all in some way touched GPU computing. In fact, we based the company on taking these very complex algorithms for computer vision and machine learning and porting them to the GPUs that were on your PC and on your smartphone. Again, company created out of environments like this with people like you, students. Now, that company got acquired by Foxconn, which is a very big technology manufacturing company, in 2018. In 2019, with students from ECE 408, we created Digital Gemini. And I'll say a few things about Digital Gemini over a couple of lectures this semester. But essentially, we were doing computational radar simulation for radars that end up in cars and in the automotive sector. So it's a very key sensor if you're building a automated driving system, an autonomous vehicle, right? You've got LiDARs, you've got cameras, but you've got an array of radars that are just sensing the world. So Henry Hase, Yuanzong, Yumai Sun, Kei Sun, I think all of them were ECE 408 students. In fact, Henry was an ECE 408 TA. We created Digital Gemini, and we sold it to Under, which is a radar chip company, just this year. And then a couple other companies, Stephen, ECE 408 student. In fact, I remember Stephen very well. He sat right where you're sitting. So I'm not putting any pressure on you, but in fact, Henry, I used to think, Henry would sit right over here. This was the semester after Stephen. But I kind of remember, it's that front row crowd that's got, that extra something special here. So Stephen went on to create, with JP, John Paul, who is an alum, create a company called Rock Metro that is building mobile apps. And if you've used, I don't know if any of you use it, but there's an Illinois app, right? Actually, Rock Metro and JP are part of that Illinois app team. So again, a team, a company created by students from ECE 408 that I helped organize and create this company. Trova, Yucheng, Chuck, Shuchen, all ECE 408 students. That company is still going, and it's basically doing AI and ML for predictive analytics for manufacturing. What's the point? That's what I do these days. I spend a lot of my time helping students create deep technologies, find investment, create companies, and help them grow. So if that's something that's interesting to you, do well. Sit in the front row here, and make sure we get to know each other. All right, and I'm serious, right? I really would appreciate the opportunity to work with anyone who's thinking about taking deep technology into the marketplace. Okay, let's move on. Any questions, by the way? Yes.
What project do you feel most proud about? Which one gives you the most memories, the most memorable memories regarding?
You want to know? This is sort of like deep psychoanalysis about me at this point. I only remember the bad parts. The bad parts, right? Like I have horror stories. I was the CEO of this company. Every good company goes through bad moments, right? The world is rosy every single morning you wake up. So there were moments in this company where we were like 2 months away from being bankrupt. And we have 40 employees. Okay, what are we going to do? So, there are moments like that, and those are the things that stick in my mind. But of course, there were lots of rosy moments too. I think all of them, in some way or form, because they're so very different, right? For me, the learning experience is really the memorable bits. So if you're interested, and we'll talk more about this, kind of the projects I'm starting to develop now are very much around the sustainability area. And I'm developing one right now. In fact, I have 2 projects I'm developing. One is around greenhouse gas emissions in data centers. And the other one is on space electronics. So, lots of satellites going up, building chips for those satellites is a project I'm also trying to develop right now. Okay. So, again, we'll talk more about this. Let's get back on track in terms of the topics for the course. So my co-instructor, Vlad, Professor Kindratenko, has been here for a while as well, and he's part of NCSA, which is the National Center for Supercomputing Applications. He's the right guy to be teaching a course like this, because a lot of you will go on, or many of you will go on to do things involving research, where computation is a key part of that research. So Vlad supports that kind of research by looking at innovative computing systems, like this one here, where there's lots of GPUs that are part of it, or this other one here, Hell, which is still in use, with, again, lots of GPUs. So if you do any sort of computational research involving physics or biomechanics or chemistry, all these things these days involve a lot of computation. Well, the underlying systems are managed by NCSA, and Vlad is part of that organization. Okay. So let's get onto it. Like, what are we here for? So at this point, what I would expect of you is that you've got familiarity with coding. Okay, and it's a coding course, right? You're going to write code, you submit your code, you're going to test your code. And as a basis, we're expecting some familiarity with C++. Okay, we're not going deep in C++. Like, we're using the basics of C++. Arrays, pointers, functions, not a lot of class, template, that kind of thing. All right, so even if you're not proficient, you'll need to get there over the next couple of weeks. Okay, you're going to be writing code that's hundreds of lines long, not thousands. In fact, in the beginning, it's much shorter, but it's complex. There's a lot of mental, here's a square matrix that you've got to turn a corner and transpose mentally before you write any code. Here's an array, two-dimensional array, that you've got to convert into pointer notation because it's the only way to parallelize it. Okay, these kind of transformations are what you need to be comfortable with in C++. Let's call it C, because it's more like C than C++. And what we're going to do is we're going to talk about taking that code and making it higher performance and much, much more parallel. Okay, you're going to write code that will run in parallel. It will run on GPUs. It might even run on the GPU that you have on your own PC or laptop, if you have the right kind. Okay. So, and these are things that you can, that you might do when you graduate, whether you work for a company or you do it as part of your research. So I hope it's practical for you, all right? So kind of the subjects we're going to touch upon, kind of parallel programming basics. We're going to look at patterns of parallel algorithms. In fact, that pattern idea is really what this course is structured on. We've got 8 patterns. Actually, no, fewer than that. 5 patterns, I think, let's say. From a vector add, a matrix multiply, histogram, scan, sparse matrix. These are patterns that you're going to explore in the programming assignments. Okay? And along the way, we're going to spend a lot of time on an API, a programming API called CUDA. Okay? And we have to do it. We got to pick something so you can write code. And CUDA is one of the popular ones out there, but it's not the only one. In fact, more and more that are relevant and successful are coming out. But the one that this course is based on is called CUDA, C-U-D-A, from NVIDIA. And it's like a lot of things, right? Once you learn CUDA, all the other ones are like first cousins of CUDA. So they're very easy to pick up once you understand the basics of any one of them. Okay, and along the way, we're going to be exposed to some ideas in computer architecture around parallelism. In fact, we're going to see some today as an example. Okay. Okay, any questions about this? Again, this is background. Yes?
Do we need a computer with a GPU to participate in this course?
Do you need a computer with a GPU to participate in this course? No, you do not. I'm not even sure if it helps you. Because we will provide, again, all the resources you need, except you do need a client PC. Okay, you need something to write your code on. I mean, there's labs here if you don't have one. So either you use the labs or you use your own. But we'll get into the details of it. So you'll write the code on your own laptop, let's say, and then submit it basically into the cloud to be executed. We'll go into the details in a moment. It's a good question. Yes?
Will you be using Python as well, or it's only C++?
Will you be using Python as well? You know, I think I started the summer thinking, hey, we should introduce Python in this course, but we never got there. Okay? So, no. I do want to point out, though, that CUDA, one of the big announcements of CUDA is that now they support Python, right? In fact, I'd like to say that we might introduce it, but by and large, right now, it's all not Python-based. I think you get a better appreciation of CUDA when we're programming at the C++ level. Yes?
Will we get our scripting environments by running something like Putty or like an online alternative?
All the code we're going to give you will be given via GitHub. Okay, so you'll clone our repos. Everything you need, scripts and otherwise, are all there. Okay. Yeah, question in the back.
So if we're not using Python, then the techniques that we learn here...
I'm going to need to come up. I can't hear.
So if we don't use Python, then the techniques that we learn here can be applied to Python codes?
Yes. Yeah, in fact, the CUDA Python API, all right? So his question is, okay, we're going to spend all this time running C++ code, but will we be able to apply what we learned to Python? Right, that's what you're asking, right? And it's yes, because the core of it is not C++. The core of it are the first 2 points, okay? And these apply to Python, to JavaScript, whatever. Okay? Okay, good. Good questions. Let me talk a little bit about the web resources now. There's a link up there that is our primary way of communicating with you. Okay, it's the course wiki. And let me just show you the course wiki quickly. It's right here. wiki.illinois.edu, and you should be able to find ECE 408 from there. What you will find here, I think the main thing is the class schedule. The link is not working. Hang on one sec. There it is, class schedule. Okay. This basically has like all your responsibilities and our responsibilities for the semester in a nice, clean, tabular form. Slides, videos, programming assignments, due dates, they're all here. Exams, okay? And we're going to treat this as the authoritative source. Like if we make any changes, we'll put the changes here first. Of course, we'll tell you, maybe by email or campus wire, but we want to treat this as like the definitive. All right, so today it is up to date. Everything is where we would expect. And what you can find is all the labs. and their due dates, okay, are also right on the schedule. You can click on the GitHub link, which is not yet active for device for Lab 0, but it will be on Thursday. And at that GitHub repository, you can clone it, look at the README file, which will tell you what you need to do exactly, and then just go from there. Okay. I'll tell you a little bit more about Lab 0 in a moment. The exams are here as well. And just for your own notice, October 11th, exam 1. And December 6th, exam 2. And that's it. There's no final in this course. Well, really, this is the final. Okay. Exam 2 is the final. But it's, I think, the last class period, or the day of the last class period. Okay, any questions on this? And again, it's, right at the wiki site. There's a question way in the back. You may need to speak up. Is midterm 2 cumulative? It's heavily oriented towards material since the first midterm. Okay, but we'll go through those details later. There was another question here, maybe the same question.
Yeah, the same question.
Okay, good, thank you. All right. Okay, so the other way we're going to communicate with you is through CampusWire. And previous semesters, CampusWire was super active. If you've got a problem with, for whatever reason, your CUDA code isn't compiling, you're welcome to post there and seek help from everyone. Students that are taking the course will often post helpful hints. The TAs are often on CampusWire a lot, so they'll respond. Sometimes Vlad and I will respond. So CampusWire is the place to go to, and I think every course uses some discussion board, and you all know how well those things work. Last bit of platform we need to use is Canvas. Okay, we will use Canvas for giving you grades, like your grades will be posted on Canvas. The exams will be administered through Canvas. And then also, with each lab you do, you'll write the lab, you'll test the lab, you'll submit the lab, and then you'll also answer a few questions about the lab on Canvas. Okay, it'll all be clear. We're going to go through this for Lab 0. And then when we do the project reports will also be done on Canvas. Okay, so that's that. Grading. This hasn't changed at all from previous semesters. Question.
Do we need to install like ProctorU to take exams, or like how are those proctored?
Those exams are, no, I'm not a big fan of ProctorU. In fact, our strategy has been this. And it's going to sound a little cruel, but that's what it is. You have a very tight time limit. You don't have time to cheat. Okay? That's it. I mean, I'll keep it that simple. Okay, so the breakdown is as such. 40% on the exams, labs divided up 35%, and the project 25%. The median for the course is a B. Okay, I hate to say that, I hate to think of this course as an easy course, because every time I come and teach it, I think everybody should do well. And we kind of curve everything that everybody does well. But nonetheless, some of you don't do well. And that always is disappointing to me. If everybody gets above a B, everybody gets above a B, and the median will be an A. It doesn't matter to me. Okay, but when I have taught this course in the past, kind of the median ends up at about maybe a B minus B. Okay, so set that as your expectation. Try to your capability, and we are here to help you get through it. Okay. Any questions on this? Yes.
I believe historically the project was both offered as a group project and also solo. This semester, do you know?
It's solo. It's solo. Yeah, it's just hard to administer the project with 320 students in a group. And I think it's actually a good individual project. So that's what we will do this semester.
Thank you.
Yep. Okay. Yeah, question.
The question is kind of related to previous slides topics. So we're learning massive parallel programming, and now that CPUs are also getting more and more cores, like we can see 128 cores threads CPUs. I know that GPU and CPU have very different architectures.
Yeah, so he raises a very good point, and I'm going to talk about that in a moment. Okay, if we get there, yeah, we're going to talk about that in a moment. So his question was, hey, CPUs have lots of cores too. Are we applying what we're going to learn here? Will it apply to the CPU world, or how are they different? And we'll get there. Okay, but that's a very good point. Okay, academic honesty, I do need to spend time on this, unfortunately. The code you write, the code you submit needs to be your own code that gets processed through your own brain and out your own fingers, okay? So no cutting and pasting. It's important, and we are very diligent about this, okay? Now, that said, right, of course, people talk about the code they're going to write with each other, and that's fine. You can talk about it. You can ask for advice from the TAs or from your classmates. That's part of being part of a team, a group. But at the end of the day, the code has to be yours. Okay, it can't look the same as this other person's code at some threshold. And we're going to check for that, right? So please don't do it. Clearly giving help, receiving help on the exam is unacceptable. And on that, we are very diligent. We're not using ProctorU or any other thing that's going to watch you as you do the exam. The exam you'll just do on your own in your own environment. That's fine. But we are going to be very diligent about checking for impropriety there. Any cases of dishonesty, we'll file with FAIR, and then we're going to seek whatever penalty is appropriate from there onward. Okay. Any questions? Yes?
Do we have exam times decided?
They'll be in the evening. Okay, but when in the evening, we're still working that out. The reason we're going to do it in the evening, just so you're all aware, right? We have a group of students, like 45 students, at the ZJUI campus in China. And we want everybody to take the exam together, right? This way, it's not like somebody's taking the exam 3 hours later with the benefit of having whatever information spread over, right? So everybody takes it together, and then it's done. So it'll be in the evening on the days that I have scheduled it. A lot of material for this course is available online. We have a book, textbook that the course is based on. In fact, this course originated with Professor Wenmei Hu, and David Kirk. This was the very first GPU programming course offered anywhere. Let's say the 2011 timeframe or 2010 timeframe. Okay. And David was the chief scientist at NVIDIA. And Wenmei, some of you may know Wenmei, was a faculty member here who recently retired, but he's still around. So Wenmei and David taught the course initially, and they created a textbook upon which the course is based. A lot of the slides, examples, etc., come directly from that book, and if you want a nice reference, get that book. Some of the chapters we provide to you for digital download right off the website. Okay. And as well, there's a NVIDIA CUDA Programmer's Guide if you're interested. And then there's a lot of material available online. Let's quickly talk about the schedule for the first 3 weeks. Because after the first 3 weeks, we'll be on autopilot. Okay. So week 1, we're here, lecture 1 today. Thursday, we're going to talk about CUDA as an intro. And as part of this first week, Lab 0. Lab 0 is due on Monday. Okay, just as a note, it's due on Monday. All the other labs are due on Fridays. So Monday, what you're going to do is you're going to install this piece of software called RAI, R-A-I. And what it is a little command line interface that you will get running on your own Windows, Linux, Mac device that you use. I don't think we have iOS, unfortunately, or Android, but that's fine. And what it does is it takes your code, which you'll create a repo for your code. You'll clone our repo and just modify the code that we give you as a starting point, and then submit using RAI. And what will happen is your code will get packaged up, sent off into the cloud, where we have GPU resources, compile, execute, we'll run some tests, and we'll send the results back to you. Actually, we'll keep the results in the cloud and give you a link that you can then go view them. Okay? So what we're trying to do is just make it super easy for you to write your code, but still give you a proper environment to do that. So Lab 0 is just a way for us to make sure that all the kinks are out of the system, for you and for us. So Lab 0, there's really not any coding involved, but you'll install RAI, you'll run some code that we give you, and we'll just make sure the process is working on your end. Okay, and that's due on Monday. Question? Is there a limit on the number of times that you can run your code? Please don't make us do that. Okay? No, I'm serious about that because right now, no, there's no limit. And these codes that we're giving you run pretty quickly, right? So it's not like you're going to send a piece of code and it's going to take an hour, which means an hour that no one else can run their code. But, just use it fairly. There's a timeout there as well. None of the code we're giving you should take more than a minute or two. So there's like a 2-minute timeout. So if it takes more than 2 minutes, your job will get killed anyways. Okay? Week 2, week 3 follows a very similar template. Lab 1 will be due a week from Friday. Week 3, Lab 2 will be due 2 weeks from Friday, and so on and so forth. Okay. In the US, for any students here on campus, the labs are due at 8 p.m. US Central Time on Fridays. ZJUI students, 8 p.m. in Beijing time. Okay, Lab 0, due on Monday, 8 p.m. Right now, there's nothing there. We're still setting it up. We're giving everybody accounts so that you can access our GitHub repository. And once it's there, you'll see the link on the wiki. We are expecting it to be available Thursday morning, okay? Thursday morning before we show up for class, it'll be there. So you'll be able to go to the link, you'll see the GitHub repo. The README will tell you exactly, step by step, what you need to do, okay? So hopefully, you guys can navigate through all that. Okay, does that make sense? Is it clear? Any questions? Yes? It'll be at least a week, okay, but a week, let's say a week. So if you turn your thing in on Friday, that Friday or maybe that Monday, the lab will be available, okay? All right? All right. Let's talk a little bit about the heart of the course. All right. So, you know, I used to introduce this course this way, that there's an old paradigm. And in fact, I find that old paradigm is like really old now. But in the way we used to do engineering and even science, there was an old paradigm where we can only do things that we could measure. We'd build something that would measure the world, and we would use that measurement to improve the state of affairs. Okay, in fact, you can't improve anything unless you can measure it, right? It's very clear, right? If you've done any sort of engineering, the only way engineering really works is that you measure. The only way we were able to measure before is by physically measuring. That's the old paradigm. We built physical instruments to do these things. The new paradigm, and this may seem very obvious to you, but it's profound. It's not just about physically measuring, but it's about being able to compute that thing. And the compute part of it has become so dominant that we almost don't even think about it anymore. I think there's very, very few instruments in the world that are physical. They're much more computational. All right? And when you think about things this way, the need for computation underlying everything that we measure and build, it's in fact the reason why this course exists. Because the computing part dominates the physical sensing part. I'll give you some examples. In fact, the one profound example that I get moved by, and I put old in quotes, because this is not old. In fact, this seems very new. But this is part of the old paradigm, right? Anyone ever seen one of these things? A couple of people are nodding their heads, right? If you've ever been in an area where one of the Google or Cruise or there's a number of companies, Waymo, vehicles kind of are driving around, right? What you see is basically a piece of metal on wheels with a lot of spinning gyro thingies and LiDARs and cameras, and it looks weird. And why is it doing that? Why do you have all that stuff? Well, clearly you got to measure the physical world in order to be able to create something that can navigate that physical world. And for a very long time, for many, many years, tens of years, Google and Waymo and Cruise and these companies that are building these autonomous vehicles were mapping and collecting data. Why were they collecting data? Sorry? To create models, right? They were collecting data of the physical world using physical apparati, because they wanted data. That's the old paradigm. Let me show you what the new paradigm looks like. Oh, I lost the video. Oh, well. Anyway, this is a video. Clearly, it's not of the real world. It's a simulation. In fact, it's a simulation created by NVIDIA, of all companies, where it's a virtual world in which you can drive cars and collect data as if the car were driving in the real world, right? So we don't have to build the models by putting a real object in the world and having it collect that data. How about we put the data collection in an artificial world and collect the data computationally? That paradigm, by the way, I told you about a company, Digital Gemini, that we sold to Under. That's exactly what that company was doing, was creating models in which you can put a car with some radar systems and collect the data as if that car were driving, on the city streets of Austin, Texas. But it's virtual Austin, Texas. So my point is, the old paradigm is put a car on the road and sense and collect and gather, which is expensive and slow. Or put a car in the virtual world and make the virtual world as close to reality as possible. Grand Theft Auto, right? Is teaching our cars to drive. That sounds funny, but that's actually what's happening. That's the new paradigm. Now, examples of this paradigm shift, they just go on and on. The way we build semiconductors used to be very physical. Now we use computational error correction to build geometries that are smaller than wavelengths of light. Electron microscopy, where it used to be a physical apparatus, it's computational. All these things, landlines, phones with wired connections, now it's all pure digital. When you do a Zoom video conference or a FaceTime call on your phone, so little of it is of the old paradigm. Okay, so why is this happening? And I'm going to talk a little bit about what to you may seem like ancient history. Okay, but it is the reason why we are here now. And it starts with this wonderful phenomenon that was true for many, many years called Dennard scaling. Okay, you know, many of you are not double E's or have any circuits background, but this is a very simple concept. All right, so when we build semiconductors, you all have heard of the idea of Moore's law and scaling. So if in year X, we are building transistors that are this big, clearly they're not this big. The gate length of a transistor, let's say, this big. In year X plus 2, we shrink that gate length. X plus 4 shrinks even more. Usually these shrinking factors are like factors of 2, okay, or 1.8. So every fixed number of years, we get to shrink that gate length. And the benefit of shrinking that gate length is that we get to put more transistors on a die at the same cost. Like if I keep my area the same, I get more devices. The more devices, the more compute. Right? That is the idea of Moore's law scaling. Now, Dennard scaling is another benefit that maybe you don't know about. Okay, so the scaling, lambda, right? So let's say my lambda here is this big, my gate length. X plus 2 years later, I get to shrink that gate length by some factor. Let's call it alpha. Okay, so I shrink it by alpha. And what happens is my voltage, how much voltage I need to apply in order to work that transistor, also scales by alpha. So alpha clearly is less than 1. Right? If I'm shrinking, that's good. I need less voltage. There's less capacitance. Good. Capacitance is usually a parasitic thing, right? It's slowing things down. My current goes down. That's all good. Everything is scaling nicely. Delay goes down. Scales by alpha. which means that frequency goes up because it's 1 over alpha. Now, the power for each transistor goes up by a factor of lambda, or by scaling factor squared. Just if I work through all the equations, CV squared times F goes up by alpha. But the good thing is, because I'm putting more of these things on a unit area, the total power for my chip stays the same. That was one of the great things observed by Dennard and his colleagues back in 1974. This is ancient history. So what that meant is, okay, Moore's law lets us shrink. Dennard scaling says that, okay, we keep shrinking, per device power goes up. I'm sorry. Per device power goes down because alpha is less than 1, it's squared, right? So per device power goes down, but I'm putting more devices on the same area, in the same chip area, which goes up by a square of the number of devices. Power stays the same. So if I build a 10-watt chip in 1974, that same 10-watt chip is just getting, 10-watt chip that I scale and put more stuff in, just gets more and more powerful for those 10 watts. Okay, and that's the idea of Dennard scaling. And that held true for many, many years. Okay, up until a point where it didn't. Okay, and kind of if you look at the processor trajectory over the years, what happened is we were designing processors. These were the CPUs, where we were increasing performance by increasing frequency, and then at a certain point we were going. Clock speed started to increase because consumers were saying, "Hey, I want a 2 gigahertz CPU instead of a 1 gigahertz CPU," and so on and so forth. Anyway, let me get move a little past this. So right around 2000, let's say 2005, what happened is the industry decided that we could not keep things moving forward because Dennard scaling was breaking down. Meaning, if we went from a process geometry in 2005 to the next process geometry, which means that we're scaling the gate length, that our power was increasing because the scaling wasn't holding. There's a lot of reasons why the scaling didn't hold at tiny geometries. We'll get into that later. So companies like Intel, Qualcomm, AMD, companies that make the silicon that powers the world, were faced with a bit of a dilemma. We can't continue to make these processors faster in the same way because the scaling is breaking down. We can't put as many transistors on the chip without the chips overheating. So what do we do? At that point, the world had to go multi-core. Okay, so we saw the world's first multi-core chips, commercial multi-core chips, right around the 2005 timeframe. 2 cores, 4 cores. Okay, and then right around the same time, the idea of a programmable GPU entered the market. If you're going to have to write multi-core code to use these multi-core chips, just embrace the parallelism and use 100 cores at the time. Okay, so 2004, 2005, 2006, 2007, multi-core CPUs and the arrival of the programmable GPU with 100 cores. Okay, and that's where we saw a distinction between what we're going to call we'll get into that. But so what we started to see is multiple cores lessening of a use of high clock frequencies, lots more threading, systems on a chip, 3D packaging. Okay, let's talk about the specifics here. So just as an example, right? If you look at a CPU, a historic CPU, let's say from this 2003 time frame, what you would see is that CPU is just a CPU. It's a processing engine with some memory. But if you take a look at a modern chip, and already this Qualcomm 880, 888 is a few years old, but what you find is it's just not a processor. There's a processor, but there's also a sensing hub and a security thing and this, and an RF system, interconnect system, memory. It's an integrated device where, in fact, this one has a GPU built in, a processor and a GPU. And that's the trend, right? If you look at the Apple chips, the A11, 12, 13, 14, it's a processor plus a bunch of other stuff, including a GPU. So this pairing of CPU and GPU now is just commonplace. Okay. So what's the difference? Somebody asked back there, what are we doing differently between a CPU, code for a CPU versus code for a GPU? So, and it comes down to this. The way we design CPUs is really about being latency optimized. I write a piece of code, and the objective of the CPU for that piece of code is to just finish that piece of code as quickly as possible. Latency. All right, so historically that's been the case, that CPUs are latency driven. So they have large caches so that we can store the data that we need close to the processing elements, so we don't have to incur the very long latency of getting it from the memory system. Okay, we have things like branch prediction, data forwarding, and speculative execution, all these good things that the CPU world invented to combat latency. Okay, and what that does is it creates a large CPU, right? In order for us to combat latency, we put a lot of highly sophisticated things in the CPU, which creates a large CPU. There's no way around that. GPUs take a very different approach. In fact, let's think about it this way. One way to approach the world is, I've got this thing I have to execute, and there's only one of it. So I'm going to try to minimize the amount of time it takes, and I'm going to work on latency. The other side of the world is, I don't have one, I've got more than I can imagine. Right? Those are the polar opposite ends of thought here. I have one, I have so many that I cannot imagine building enough resources to execute them. In fact, for many of you, you're thinking, there's nothing in the world that fits that. And you're wrong. In fact, you're so wrong that you need to clear your mind of that thought. So many things that we try to do these days are compute limited. Compute limited to the point where we have hundreds of millions of threads. Not one thread, hundreds of millions. More threads than I could ever imagine putting onto this single chip. And that's the perspective we're going to spend the next 15 weeks in. And it turns out that lots of the computation in the world fits within that paradigm. Okay. So, well, if we're thinking on that end of the world, how do we build our system? We think throughput. I've got 100 million threads. I have 1,000 cores. So my job is to take those 100 million threads and make sure that I'm utilizing as much of this silicon area as possible to get those 100 million threads done. Okay, so, well, what does that mean? It means, hey, don't put any memory, or put as little memory on this thing as possible, because we're going to fill it up with things that actually compute, cores. Keep the cores simple as possible. Branch prediction, gone. Data forwarding, gone. Speculative execution, gone. Anything that's sophisticated, latency-oriented, gone. Okay? And then, well, what about the latency? Like, I've got one of these 100 million threads, I put it on one of these, computing elements, and what happens when it stalls? What happens when I need something from memory and I can't make any forward progress? Well, what we're going to do is we're going to take that thing, we're going to throw it to the side. We'll get another thread and we'll put it on. And we'll do that so fast that we're not going to lose any cycles. Okay, so now you see the shift in paradigm here from the old way of thinking to this new latency throughput-oriented way of thinking. Now, this is not an architecture course, so we're not going to spend any significant time thinking about the architecture, but we're going to think about it from the point of view of the programmer who needs to program those 100 million threads. Okay, that's what we're going to spend the next 15 weeks doing. Okay, and it's, like I said, it's going to be different. Just to drive home a point, right? It used to be when I was in your shoes as a student, the world's most sought-after company that people like me wanted to go work at was Intel. It was the Silicon Valley company. Yeah, when you told your friends you were going to Intel, they were jealous. It's not quite the same now, is it? The world is really kind of different now, and in fact, companies like NVIDIA are starting to take the place of what Intel used to be. In fact, nowadays, maybe it's not even NVIDIA anymore. And in the silicon world, it's companies we haven't heard of yet that are building, deep learning accelerators. But those companies look a lot more like this than that. And it's, this is sticking. This idea that you're going to build these really tiny cores instead of these very large, this chip, I think you can probably see 1, 2, 3, 4, 5. Maybe that's not cores. So 1, 2, 3, 4, 5, 10. So this thing has 10 cores in silicon. Here's one. Compared to 3,456. Roughly about the same size. Roughly, actually, 2 process generations difference. So not apples to apples, but close enough. Okay. So, I'm going to finish up here by talking about how we're going to approach things. Like, what are you going to be doing this semester? What you're going to be doing this semester is essentially following a workflow where we're going to take like the most compute-intensive parts of common applications, and we're going to put them into CUDA, where we're going to see maybe not 100 million threads, but thousands, hundreds of thousands of threads that are active at any one point. Okay, you're going to write the code to do that. And it's going to turn out that the code you write may not be the most efficient code. In fact, it may be slower running on the GPU than on the CPU. This often happens. And what we'll do is we're going to go through a series of steps to take that code and make it run more efficiently on the GPU. Process called performance tuning. Okay, and that tuning really gets to the heart of what makes parallel programming challenging, really. So we're going to spend some time doing that tuning. Okay, so let me give you an example. So, little piece of C code right here. Okay, n loop iterations, and in each loop iteration, we're going to take an element of A and add it to an element of B and store it into an element of C. Now, if you're coming from the single-threaded world, that looks like a pretty straightforward piece of code, right? And when you look at it, you might think, well, it's single-threaded, right? Every loop iteration executes after the previous loop iteration. That's what I equal I plus plus, or I equal I plus 1, I plus plus does. But the guts of that are parallel, right? In the computation of any element of C, I don't need the prior iterations of the loop. So what we today kind of encode as a serial computation, we need to encode as a parallel computation. That's going to be the simple part of the semester. Okay. Just kind of expressing that as parallel. Let me ask you a question. Let's think a bit. So what if sorry, I didn't. What if I replaced the inner loop with that? Okay, so now we look at that. So C0 equals A sub I plus C0. Is that parallel? Yeah.
We make a vector that is just all C0 and then add a vector of A in parallel. And then we have to have another step of summing them up. Because you're only storing...
Okay, so you're a smart guy, right? Because you know the answer is it's not serial. But you haven't figured out why. So you're half smart. Yeah.
You can balance the expression so that you can sum the first half of A and the second half of A separately.
Okay, no, he's gonna, the two of you would make great partners, right? So he's filling in for where you didn't carry on. So what he's observing is, well, hey, this is expressed this way. It looks like a serial computation. I have to take, if I unfold it, it's A0 plus A1 plus A2 plus A3 plus A blah, 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 all the way to AN minus 1 added to C0. Right? That looks like a very serial computation. But it turns out that addition is associative. Right? I could take that big chain of adds and break it into two pieces. Then I can take those little chains of adds and break them into two pieces, and two pieces, and two pieces, and two pieces. And then all of a sudden I've got something that's not quite that nice, but it's a lot less serial than that thing that I expressed right on the slide. By the way, that's going to be programming assignment 5.1. That right there. Okay, what's the point? That sometimes the parallelism is like staring us in the face. Sometimes the parallelism is not staring us in the face. So we have to go and find it and extract it by being clever. Okay? Thankfully, there's a lot of the former, but we will always be limited by the latter. Because the easy stuff we can all get. It's the hard stuff that's going to differentiate us and push us forward, right? So it gives you a couple of flavors of things here. Okay, let me stop here for the moment. And any questions? Yeah.
So a question that I just had about that, just that example, or just this, I guess, parallel programming in general. Are we going to cover like determining the, I want to say the efficiency of actually offloading our code to, say like to the GPU, like, and then benchmarking that against whether it's just faster to do it wholly on the CPU?
So his question is, are we going to be benchmarking code that we write for the GPU to see if it's better than keeping it on the CPU? Maybe I'm paraphrasing a bit. And the answer is yes. In fact, the project, we're going to take a deep learning kernel, convolutional deep learning thing. We're going to put PyTorch and TensorFlow aside, and we're going to write our own low-level GPU-driven convolutional deep neural network. And when we do that, we're going to realize, hey, we put pieces of this on the GPU, and it's not going to make sense. We should have kept it on the CPU. But then pieces of it clearly fit on the GPU. And understanding that trade-off is what that final project will be. Okay, very good question. Yeah, you may need to speak up. I won't be able to hear you.
When we're learning about programming on the GPUs, will we have to work with like blocking and synchronization for shared real estate, or is that?
That's a great question. So his question is, when we program on the GPU, are we going to worry about blocking and synchronization and all those things? Maybe you don't even know what they mean. And the answer is yes. We're going to deal with them in the world where the parallelism is abundant. Okay? So we will need to do those things to make sure our code works correctly. So we'll learn them along the way. Yes?
So I understand that there is a broad aspects of application that we need to use parallel programming. And so it says in our reading material that there is now a great need for software developers to learn about parallel programming. So my question is, can we develop a tool to automatically transform, serial programming code into parallel programming? In the future, will this be a problem for the operating system to deal with? Like, everybody still write about serial programming code, and we don't care about parallel programming, and the system just
Does it for us. Yeah, I think if you could do that, you would be a highly successful person. Okay, so his question is, can't we just have something automatically parallelize our code for us? And the answer is, we've been trying. And for a good reason, right? Because writing code sucks in the first place, right? It's fun, but it's hard. And if we have to write parallel code, it's even harder. Wouldn't it be great if something did it for us? The answer is yes, but we haven't found it yet.
So what's like the main difficulty that we encounter?
Because the code, how do you convert this into a tree?
So this is like, dividing this task into a...
Right, so the problem is there's no one template that's going to work, right? Coding is so amorphous that it's hard to come up with a single solution that works. Okay, we'll see you on Thursday.